in this lesson we're going to talk about related rates. We have related rates when we are working with multiple variables that are linked through a relationship, but each of those variables have a dependency on a specific independent variable such as time. So most of the examples that we're going to work in this application of implicit differentiation and the chain rule are going to be related to situations when our variables, for example, volume or speed or mass, are going to change with respect to time. Let's illustrate this with the first example. A stone is thrown into a pond, causing ripples in the form of concentric circles. So we have our stone falls into the pond and we get circular waves like this, and the radius of the wave that goes away from the center, let's call that radius r, is changing at a rate, the r over dt, that is given to be 20 centimeters per second. A, when a circular ripple has a radius of 50 centimeters, find 1, the rate of change of the circle circumference, and B, the rate of change of the circle's area. B, repeat A when the radius is 100 centimeters. So in order to do the first part, A1, we want to find an expression for the circumference, and that is C equals 2 pi r. I'm not just going to substitute the value of the radius, 50 centimeters. I need to find the rate of change first. So to do that, I'm going to differentiate with respect to time. So derivative of C with respect to time is equal to 2 pi derivative of r with respect to time. And now I'm just going to substitute the rate. This is equal to 2 pi times 20 centimeters per second, and that is 40 pi centimeters per second. So as you notice, the rate of change of the circumference does not depend on the radius of the wave. So at 50 centimeters, the rate of change is going to be 40 pi. Now let's do the second part. So we want the rate of change of the area. So for the area, the expression is pi r squared. In this case, A changes with time and r changes with time. We need to differentiate implicitly this expression if we want the rate of change of the area, because none of these variables are explicitly written in terms of time. So we want to calculate the rate of change of A, and that would be equal to pi derivative with respect to time of r squared. And we do that implicitly using chain rule. So the derivative of r squared is going to be 2r r dash, or 2r derivative of r with respect to time, and that we know is 20 centimeters. So we substitute pi times 2 times 20 centimeters per second times the radius. So that is 40 pi r, and the units are going to be centimeters square per second. Now, this rate of change does depend on the radius. Therefore, when the radius is 50 centimeters, so evaluated at r equals 50 centimeters, we get 40 pi times 50 centimeters squared per second, and that is 2000 pi centimeters squared. Now if we wanted to repeat this process, since we found that the rate of change for the circumference does not depend on r, the answer for the rate of change of the circle circumference doesn't change when the radius is 100. So in this case, we also have the CDT will be equal to 40 pi centimeters per second. However, because the area did have a dependence on the radius, we find that the rate of change of the area when t is 100 centimeters is going to be 40 pi times 100 centimeters squared per second. So that's going to be 4,000 pi centimeters squared per second. Let's do example number 2. A 4-meter ladder stands upright against a vertical wall. The foot of the ladder is pulled away from the wall at a constant rate of 0.75 meters per second. Find how fast the top of the ladder is coming down the wall at the instant it is 3 meters above the ground, 1 meter above the ground. I would recommend that we start by drawing a diagram that represents the situation. So we have our floor and we have the wall, and the ladder is going to be at some point diagonally, and the lower part of the ladder is being pulled at 0.75 meters per second. And the question is, how fast is the top of the ladder going down? So let's take advantage of this ladder forming a triangle with the ground and the wall, and let's define this side of the triangle as x and this side of the triangle as y. That way we know that the derivative with respect to time of x is the rate of change 0.75 meters per second, and the question is calling for dy dt. We don't know what this is. Now we know that the ladder is 4 meters long, so the distance from here to here is 4 meters. So we can create a relationship if we use Pythagoras theorem, that is x squared plus y squared would be 4 squared, or x squared plus y squared equals 16. If we want to know the rates of change, then we need to differentiate this expression implicitly, and we will get 2x derivative with respect to t of x plus 2y derivative of y with respect to t equals the derivative of 16 is 0 because it is a constant. Now the question is dy over dt. So let's solve that equation for dy over dt, and we get dy over dt is equal to minus 2x over 2y times dx over dt. Simplifying, this expression is x over y dx over dt. And we can substitute dx over dt with 0.75. So dy over dt is going to be minus x over y times 0.75. Now, what are the values for x and y at the moment when the y value is 3 meters? So in that case, we have 4 squared equals 3 squared plus x squared. 16 minus 9 is equal to x squared. And 7 in a root is equal to x. So substituting these values, we get the derivative of y with respect to t is minus root 7 divided by 3 times 0.75, and the units would be meters per second. That is equal to minus 0.66143, etc. meters per second, and rounding to 3 significant figures, minus 0.661 meters per second. And Our answer definitely makes sense because the negative sign is reflecting the fact that the top of the ladder is going down. Now, if we wanted to know at 1 meter above the ground, then we need to repeat the exact same process. 4 squared equals to 1 squared plus x squared. That is 16 equals to 1 plus x squared. That is 15 equals to x squared. That means x is equal to square root of 15. Again, we take the positive one because it's a real world length. And the derivative with respect to t to time of y, or the rate of change of the top of the ladder, would be equal to minus root 15 divided by 1 times 0.75 meters per second, and that is minus 2.90473 meters per second. Now to three significant figures, that would be minus 2.90 meters per second. Now for a final example. A spherical piece of ice melts at a rate proportional to its surface area. The ice remains spherical while melting. Let the radius of the ice at time t equal r of t. Write down the volume V of the ice in terms of r of t. Then show that the r dt is constant, and see if the initial radius of the ice is 5 centimeters and 100 seconds later it is 4.5 centimeters. Determine the length of time it will take the ice to completely melt. So we're going to begin by writing the volume of the sphere. So V is going to be 4/3 times pi radius power 3. Now B, we are given at the start of the problem that the ice melts at a rate proportional to the surface area. So that's going to be key for B. So we need to find the derivative of the volume, and that is going to be derivative of B with respect to time is equal to 4/3 times pi times 3 r squared times the derivative of r with respect to time. The problem says that the volume changes in proportion to its surface area, and the surface area of a sphere is given by 4 pi r power 2. Therefore, the expression for the volume that I found, which is dv over dt equals 4 pi r squared times dr over dt, should be equivalent to Ka, where K is going to be a constant. Now, since the surface area is 4 pi r squared, then it means that the r over dt must be constant. Now we're going to do C. We know that it takes 100 seconds to melt 0.5 centimeters. That means it would take 200 seconds to melt 1 centimeter. And since we have 5 centimeters total for the radius of the sphere, then it's going to be, the total time is going to be 200 seconds times 5, and that is equal to 1000 seconds.